Okay, so let's start with this mesh current analysis, and as with the branch current analysis that we discussed in the recent weeks. The prerequisites for this, we know all active and passive network elements, and we also know the network structure. And so then we want to calculate all the currents and voltages in the network. Hello. So they are to be calculated, and another prerequisite that we need for this mesh current analysis is that the network only contains voltage sources, no current sources. It's not impossible to also take a look at current sources in this method, but it's not that straightforward, and so we will only look at voltage sources. So if you have a network with current sources, take any other of the methods that we looked at, for example, nodal voltage analysis, which perfectly worked fine for circuits with current sources, but not really for voltage sources. Okay, so then once again we form a system of equations, and we do not really calculate the branch currents, we calculate these so-called mesh currents. And for this set of or system of equations, we use Kirchhoff's voltage laws and the current voltage relationships at the network elements. So for us, this will be Ohm's law, because we only just take a look at resistive networks. And so we also, of course, need the Kirchhoff's current laws, but they are included by using these so-called mesh currents. What this means, we will see in a second. Okay, and so then the advantage that we get is that we reduce the number of unknowns in our system of equations in comparison with this branch current analysis, because at the end we only have Kirchhoff's voltage laws, no Kirchhoff's current laws anymore explicitly in the system of equations. And so this is potentially, because it's smaller, it's easier to solve if you need to solve it by hand. At the end, if you take a computer to solve it, the computer won't care really how large the system of equations is. But another advantage that we will see is that there are once again rules how to set up the system of equations very quickly. Okay, so then we solve this system of equations, we get these mesh currents. From these mesh currents we can calculate our branch currents, and finally we can calculate our branch voltages from these branch currents. And then we know all currents and voltages inside the network. Okay, so that's the theory. It's always good from my point of view to take a look at some example. And before we do this, reminder how to find independent Kirchhoff's voltage laws. What was the method that we discussed last week?
Use a tree.
Yeah, use this so-called complete tree. Yeah, that was, so inside the graph of the network we need to find a complete tree. This was a subset of the graph that connects all the nodes, but without that there is some closed loop. And then by closing this tree over the remaining branches, we find the essential branches of the network. And so, yeah, if k was the number of nodes, then we get k minus 1 branches inside this complete tree, and we get a certain number of essential meshes. Okay, this is what we also did last week. So as an example, once again, let's take a look at what we already did last week, because we know the result, remember the result, and we calculated this with branch current analysis already and with nodal voltage analysis. And if you remember, the problem is this, the bad guy here is this resistance R5 in the center. So let's try to do it once again with mesh current analysis. And so for this, we will connect a source here. The source will power the circuit, and if we know the voltage here, for example, and if we can calculate the total current here at this line, or the current that goes into R1 and into R3, this will be the total current, and so voltage divided by total current will give us the total resistance of the circuit. That's the idea. Okay, so yeah, we are free to choose the source. This mesh current analysis better works with voltage sources, so we choose a voltage source. So as usual, I will copy this and paste it into my drawing program, which is already prepared here. And maybe make it a little smaller. And so the first question is, what can I choose? What could I choose as this complete tree that connects all nodes without having a complete loop?
Like a super?
Yeah, like this what we had last week. Like the vertical line here, and then this additional horizontal line is the connection of all the three nodes A, B, C, D without having a closed loop. And then we can close this mesh, we can close this tree over this branch here. This gives us one mesh that I will denote or number with 1. Then we have a second mesh, this one here, that I will number with 2. And then the last mesh, the third mesh, is this one here that I number with 3. And at the end, if the order does not matter, the direction does not matter. Of course, if you take a different order, if you take a different direction, you get a different system of equations. But at the end, the system of equations should have the very same solution. The very same should give you the very same answer at the end. Okay, so maybe shortly go back to the slides. So we have found our essential meshes, and now we need to set up the system of equations. And for the system of equations, we start, as mentioned, we start with Kirchhoff's voltage laws, and we can set them up. I won't use these colors, but or I will use the colors here in front, but not for writing all the equations because it's so thick. So we need to have 3 Kirchhoff's voltage laws for these 3 essential meshes. So what can I write for the Kirchhoff's voltage law here in the first mesh?
The source is V1 plus V2?
Exactly. So I will write V1 plus V2 equals V source. I will write the unknown quantities on the left side, the known quantities on the right side, that try to directly order them. Okay, so for the second mesh, say again? V3 plus V5, I will try to directly order then, minus V1 equals 0. So so here the current goes in this direction. So if we go along this loop, we have the opposite direction, and we have the same direction, we have the same direction. So this is minus, this is plus, we get 0. Okay. And so for the last mesh, V2 minus V4 plus V5 equals 0. Let me shortly check. So this is the opposite direction. This is, isn't V5 also the opposite direction? But the V5, wait. Now I made everything kaput here because my program sucks. Wait, I need to go to a new page and go down and up again. Then everything should be fine. Okay, so if we go this way, I would say it's but okay. Maybe you've just set everything in the opposite direction. So if we do it clockwise, then we have minus V2 plus V4 minus V5. Shouldn't it be like this? This is the opposite direction. Here it's also the opposite direction. Here it's the same direction.
She said it like minus 1.
Okay, excellent. Then yeah, it's always difficult. I always need to write it down. I cannot do such stuff, at least not in English. Okay. So now if we take a look at this equation system, and maybe I should make more sure that this is not a 5, but this is the source here. And this is a 5 This is the source. So we have now a system with 3 equations and 5 unknowns. Not so good. So next step, maybe I can try to do it here, is we now insert all these Ohm's laws. We always say Vx or Vn is Rn times In for n is 1, 2, 5. Right? Okay, so then we get R1 times I1 plus R2 times I2 equals V source. Then we get minus R1 times I1 plus R3 times I3 plus R5 times I5 equals 0. No source in this mesh. And so the last Kirchhoff's voltage law equation is minus R2 times I2 plus R4 times I4 and minus R5 times I5 equals also 0. And so you can imagine if we would, once again, for example, calculate the sum of all these 3, we would get the mesh equation for the big mesh that goes around the whole circuit, what we've also checked last time. Okay, so still, okay, now we have currents instead of voltages, but still we have an equation system with 5 equations, 3 equations, but 5 unknowns. Okay, so now we try to express our branch currents by the mesh currents. And the mesh currents are more or less virtual currents that flow inside this mesh. So in this mesh we have the current IM1, in this mesh we have the current IM2, in this mesh we have the current IM3. So we now need to express our 5 branch currents, I1, I2, I3, I4 and I5 by these mesh currents. So let's start with this resistor. This resistor belongs to this mesh and it belongs to this mesh. So there's this mesh current IM1 flowing through this in the same direction, positive, and the mesh current from the second mesh in the opposite direction. So for the first branch current, we get that this is IM1 and then minus IM2. And at the end, it's a little bit like setting up a nodal equation, a Kirchhoff's current law for this node here. And say, okay, this current here is the difference between what comes from here, what enters the node from here and exits the node from here. So at the end, this is something like our Kirchhoff's voltage law, Kirchhoff's current law, just written down in a different way. Okay, so then the second current, the second branch current, what do I need to write down? Say again. It should be IM1, right? And then minus IM3, exactly. So then the third branch current is the same as the second mesh current. The fourth branch current is the same as the third mesh current. And the current here through the resistor R5 in the center is... Yeah, it's IM2 because they have the same direction, and so it's IM2 minus IM3. And so the next step is we take all these equations and insert them here into our Kirchhoff's voltage laws. And so because then we express our 5 unknown branch currents with only 3 mesh currents, we get only 3 unknowns anymore in our system of 3 equations. So this should be there, we should be able to solve it. Okay, so yeah, I think I won't take all the colors this time, but just rewrite it like this. So we have R1 multiplied with IM1 minus IM2. Then we have plus R2 multiplied with I2, and this is IM1 minus IM3. And this is the same as the source voltage. Okay, this was the first Kirchhoff's current law, voltage law. Then we have minus R1 multiplied with IM1 minus IM2, which is once again this. Then we have plus R3 multiplied with IM2, and we have plus R5 multiplied with the difference of these two, IM2 minus IM3, and this at the end should be 0. Okay, and then the last Kirchhoff's voltage law is minus R2 multiplied with IM1 minus IM3 plus R4 multiplied with IM3 and minus R5, and this is once again also multiplied with IM2 minus IM3, and the sum is 0. Okay, so now check 3 equations, 3 unknowns, should be possible to solve. So what I will once again do is I will write this as some matrix equation. And so I need a 3 by 3 matrix, a little longer because there are many coefficients in there. Then we have our vector of the 3 unknown mesh currents, IM1, IM2, and IM3. And then on the other side, on the right side, we have the sources. And the sources, it's fairly simple. There's just Vs and 0 and 0. And so now here we need to check, right? We have some, we need to have some column that is associated with IM1. We have one column that is associated with IM2. And we have a last column that is associated with IM3. And so now, if we check the coefficients, so for IM1 we have here R1 and R2. So here we have R1 plus R2. Then we have minus R1 for the IM2 and minus R2 for the IM3. So minus R1 minus R2. Okay, so next equation we can check for the IM1, we have also minus R1. For IM2 we have minus and minus is plus R1, plus R3, and plus R5. So R1 plus R3 plus R5. And for IM3 we have minus R5. Okay. And for the last equation, we have minus R2 for IM1. Then we have IM2 is here minus R5. And so minus and minus is plus. So R2 plus R4, here once again minus and minus is plus R5. So R2 plus R4 plus R5. This is the system of equations for this mesh current analysis for our circuit. Now, if we take a close look onto the circuit and onto this system of equations that we have in matrix form, what do we see? And also hello to the 5 persons watching on Twitch. You can also write something in the chat. I have the chat here on my cell phone.
As a diagonal, we've got like all the resistances of each mesh.
Exactly. So if we take a look at first on the main diagonal of this matrix, because it's a 3 by 3 matrix, there are 3 elements. And on this first element, we have R1 plus R2, which is the sum of the resistances that we have in the first mesh. In the first mesh goes through R1 and R2. The second mesh goes through R1, R3, and R5. That's why we have here R1, R3, and R5. And the last mesh closes or goes a loop over R2, R5, R4. That's why we have here R2, R5, R4. Okay, so this is the rule to set up the main diagonal. And so we would not necessarily need to have done this here before. We could, if we would have known this rule, we could also directly have set up the system of equations. Okay, so what happens on the off-diagonal elements?
Negative resistance between each two.
Exactly, there is the, in this case, always negative resistance between 2 meshes. So here we have mesh 1 and mesh 2. They are coupled with this resistance R1. So we have, that's why R1 and R1. Between the first and the third mesh, we have the coupling resistance R2. That's why here we have R2 and R2. Right? First line, third column, third line, first column. And the coupling resistance between the second and the third node is R5. And that's why we have here R5. And usually, so if you remember nodal voltage analyzers last week, they were always negative. Always. Here, it's kind of a coincidence that they are all negative, and they are all negative because our mesh directions here all are pointing in the same direction, or they are all clockwise. If we would have selected this, let's say clockwise, and this counterclockwise, then this coupling resistor would be positive, for example, because then the mesh currents would point in the very same direction here at this resistor. And because this and this, they're always opposing each other. And that's why they're all negative, because they're opposing each other. Okay, so on the off-diagonal elements, we have the coupling resistors between 2 meshes multiplied with the direction. If they are opposite, it's negative. If they have the same direction, it's positive. Okay. And so on the right side in this source vector,
we don't have a source in the other.
Yeah, we have the sources in each mesh, and we have just one source, and this is in the first mesh. And so here we have the source, here we have no sources, and the mesh current and the source, they are pointing in opposite directions. So usually they would be negative, right? They would be negative on this side of the equation. And if we move them to the other side of this equation, to the right side, then it gets positive. And that's why here the sign is also depends on the direction of the voltage source with respect to the mesh current. And if it's the opposite direction, then it's positive. If it's the same direction, then it's negative. Here, if it's the opposite direction, it's negative. If it's the same direction, it's positive. So the sign here and the sign here, they are the opposite of each other, let's say. Okay, so now we have a perfectly fine system of equations. We know all the values. So the next step would be, after writing down the system of equations in matrix form, inserting the values and calculating the equivalent resistance in Octave. So I will try to find my Octave window, which is here. My mouse already went to sleep. Make this a little smaller. This already crashes, so I need to go back to the standard settings. Okay, and with a little luck, I have opened the same Octave version as last week, and there still should be my values in there, but not really. I think the resistors were 1 kilo ohm, 2, 3, and okay. So R1 was 1 kilo ohm, R2 was 2 kilo ohm, R3 was 1 kilo ohm, R4 was also 1 kilo ohm, and R5 was 3 kilo ohms. Okay, so now we have these values here. So then we can try to insert our mesh current analysis matrix. And matrix, we need square brackets, and we need R1 plus R2, then we need minus R1 and minus R2. Then semicolon gives a new line, minus R1, R1 plus R3 plus R5, and minus R5. And then last line is minus R2 minus R5, R2 plus R4 plus R5. And then the result looks like this, which probably does not look too bad. Okay, so then the source, we could just set it to 1 volt, for example, if we want to have this equivalent resistance at the end. And so our source vector would be the source, a 0 and a 0, and looks like this. And so now we can calculate our mesh currents by, if I shortly switch to full screen, to my t-shirt, use the very same equation on my t-shirt, and say, let's switch back to the screen share. So we need to have the matrix, the mesh current analysis matrix, and then this left division with the source vector. And so now we get the mesh currents. And so now from these mesh currents, we would need to calculate, let's see how small I can make this, not too small. So from this we would need to find our branch currents. So I will do it in 2 different ways. So we can say, okay, now our first branch current is the first mesh current minus the second mesh current. And so we get this. And we could do it for the second one. The second one is IM1 minus IM3. So this is the second. Oops, this was the first one. This is the second one. And so because we have some volt and we have some kilo ohms, we get some currents in milliampere. So the third one would be just the second mesh current. The fourth one would just be the third mesh current, and the fifth one is IM2 minus IM3. So then we get, so now we have an overview of all the 5 mesh currents here. And so our total current would be I1 plus I3, right? These are the currents that flow out of our source through the first resistor and through the third resistor. So this should be the total current. And now if we want to have the resistance between these nodes A and B, we need to have the voltage, the source voltage, V source divided by this total current. And then we get what we had last week, if you remember, the a little less than 1.2 kilo ohm. And someone commented under the YouTube video that if you do the calculation correctly, and we can try to do it with the star delta analysis, then you get like this kilo ohm. So if you, interestingly, this system of equations, if you would solve it exactly with fractions and not with decimal fractions, you at the end you would end up with this fraction there. And you could show this with the star data conversion that this works in this case. So thanks to whoever commented this under some YouTube video. Okay. Yeah, so now it's solved. Just maybe some small idea for MATLAB or for Octave here. So if I scroll up a little bit, these are the 5 branch currents that we have in this case. And we could try to make this calculation, let's say, a little, not simpler, but maybe shorter, by having another matrix. And this matrix would be called incidence matrix. And this incidence matrix would just contain these factors that we have here. So I will call this B matrix. And the B matrix would contain now in the first line 1, -1, and 0, because we need the IM1 plus, the second current minus, and the last one 0 times. And in the second row, in the second row, I cannot fit it on the screen. So here we have minus IM1 plus IM1 minus IM2. So in the second row, we have 1, 0, -1. Then we have just 0, 1, 0. Then we have 0, 0, 1. And in the last row, we get 0, 1, -1. And then the B matrix looks like this and contains all the coefficients that we have here. And so now this way, I could calculate all the branch currents from our mesh currents by taking B and calculating B with this mesh currents. And so this way I get all the branch currents in one vector, all the 5 branch currents. And now, don't know if this fits on the same screen more or less. Yeah, so the first one, you can see it's interesting. It's not the same result. Doch, it is the same result because this calculation was wrong. I've scrolled too much upwards, but this is the right one. This fits. The second one fits. Third one fits. Fourth one also fits, and the last one also fits. So working perfectly nice. Yeah, and so then. Then we have all the branch currents. And now the last way would be to find all the branch voltages if you would like to have the voltages. And so now once again, you could say, okay, V1 is the first branch current times the first resistance, for example. Yeah, and then we would get, okay, we get this and this voltage in this case. And the easier way would be to say, okay, if we want to have the branch voltages, we take a diagonal matrix that consists of all the resistors that we have. And at this time you see, okay, it would have been a good idea to also write all the resistors just in one vector or in one matrix. So and multiply this with the branch currents. And I think I need to make this a little smaller so it's not hidden behind my camera window. Yeah, so a diagonal matrix, we can have a look at this in a second, that just contains the resistances on the main diagonal multiplied with the branch currents gives the branch voltages. So this would be all the branch voltages, and this also corresponds to what we had last week if you would check, and would also perfectly make sense because the first and the second voltage together, they give 1 volt. The third and the fourth voltage together give 1 volt, and the difference between this and the difference between this and this is the difference between, let's take a look at the circuit. the difference between 1 and 3. So the difference between these two is this one, and the difference between these two here, the 64 and the 52, is also 12. So perfectly makes sense. And this diagonal matrix here, can I copy this? No, obviously not. So if we just output this diagonal matrix, so this diagonal matrix just creates as a matrix just with the resistances there on the main diagonal. And so at the end, it's a, yeah, you don't need to have such a large effort to set up the system of equations, because you just need to know these 3 rules. Then you put the system of equations into some solver like Octave, MATLAB, Python, whatever. Calculate all the stuff there, and then you get a result, and then that's it. And so it's also a very efficient way of calculating such circuits and networks.